Okay, so I welcome you guys once again. And today we are going to look at what we call the T-substitution, right? We have what we call the T-substitution. And here we apply some of the things that we've looked at already, especially in trigonometry, because I know it was proved that if you're given T as the tan half of theta, you show how what sine theta is equal to, and also what cos theta is equal to. And still further, this one is going to take us also as we integrate, we shall be bringing in the aspects of what we've already looked at, and that is none other than the sine substitution and the tan substitution. You may be solving a question, and then there in the middle, you reach a part where you have to substitute, where you have to do sine substitution, and where you have to do the tan substitution. So it is very, very, very obvious that where it is necessary to do those substitutions, you will be just substituting, okay? So what you need to know for now, you need to know that from trigonometry, if we have T as tan half of theta, okay? If you have T as tan half of theta, then we shall need to know that our sine theta will be twice T of 1 plus T squared. And also, you need to remember that our cos theta is equal to 1 minus T squared out of 1 plus T squared. That is in accordance to trigonometry. So the general substitution of integration is given by T is equal to tan half angles. We have got two cases where the first case is this, and we shall look at also a case where we have a square value, or where we have the angles are squared, okay? So in other words, we shall use these substitutions, okay? We shall use these substitutions, but not also forgetting that we shall be substituting T as tan half of theta. Without wasting any time, allow me strictly move to examples. Allow me move strictly to examples. And examples, find one, the integral of cosec x dx. 2, we've got the integral of sec x dx. 3, we've got the integral of 1 over 3 minus 2 cos t. This is dt. Then 4, we've got the integral of sec 3 times theta d theta. Then 5, we have got the integral of 2 out of 3 sine 3x plus 4 then dx. So these are the integrals we've got to work on, and ideally these ones are very, 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 very easy. Okay, they are very, very easy. So it's a matter of knowing how to work on the trigonometric procedure to change what you have into the form that takes on the other values that we looked at. Without going too far, let's begin on solution of Roman 1. what we need to do in all cases, of course, you say that we let, in all cases, we let t to be equaling to tan half of x, since we have x here. So our t, we let it to be tan half of x. That is what you need to know. Then after that, the second step is to differentiate both sides. And when you differentiate this side, you'll get dt is equals to, when you're differentiating tan half, you first drop half, then sec squared, okay? It is half sec squared a half x, then dx, right? So when you look at this, you'll have 2 dt. If you cross multiply, you have 2 dt is equals to sec squared a half x dx, all right? But remember, this sec squared is the same as 1 plus tan squared, okay? So we shall, all these steps can be reduced. From here, you can go to the last step. So 2 dt is 1 plus tan squared a half x dx. But remember, our tan a half x itself is t, meaning tan squared a half is t squared. So we shall have 2 dt is equals to 1 plus t squared, then dx. And in this case, you can get your dx. So our dx is going to be equal to 2 dt out of 1 plus t squared. So it is after getting all this that now you can come and do further integration. You can come and do integrate. So it would mean that you also need to know, because now this cosec, remember our identities are in terms of cos and sine. So that is when we can express them in terms of t. But now having cosec would first necessitate you to first change cosec to a smaller thing or to a smaller angle like a sine, because we have a relationship between cosec and sine. So I'm going to say that the integral of cosec x dx is going to be equal to the integral of 1 over sine x, because a cosec is the same as 1 over sine. So if that is the case, then you have to substitute. So it will be 1 over sine x. Remember our sine x, okay? In this case, our sine x is the same as 2t over 1 plus t squared. That is sine x. So if we have 1 over sine x, then you will take the reciprocal also. So it will be the integral of 1 plus t squared over 2t. I guess you can know why I've made the reciprocal. 1 over sine x, and there we have sine x. So if we have sine x as twice t of 1 plus t squared, then if we need 1 over sine, you just also take the reciprocal there and then. So it is 1 plus t squared over 2t, okay? Then times dx, which dx we've seen as 2t out of 1 plus t squared. As you can see, these two will cancel and the 2t will also cancel. So we are going to have our integral, of course, here is dt, we have our dt. So we are going to have our integral as when this one cancels and this one and this one and this one, okay, we shall have, is it? No. This is just T2. Okay, this is just T2. So because we have 2 dt, so it is 2 dt over 1 plus t squared. So a 2 will cancel with that 2. 1 plus t squared will cancel with 1 t squared. So we shall have the integral of 1 over t dt. But when we integrate 1 over t, we get ln t, because when you differentiate t, you get 1. So we just say that this is ln t, of course, plus a constant of integration. But remember, t is the same as tan half of x, because after all, it has to go back to the initial variable, which is x. So it would mean that therefore the integral over cosec x dx is the same as this is the same as ln. Then instead of writing it, we shall say tan half x then plus a constant of integration. So that is what we get as our integral after integrating ln, rather after integrating a cosec. Then from there, let's differentiate a sec. After this, I would love to go first to this, then there we can catch up to these ones of this nature. Okay, so let's integrate a cosec. Let's integrate a cosec. A sec. Okay. So we have Roman 2 where we are integrating a sec x dx. To integrate a sec, of course, we shall need still to let, and we are going to let still we let t, all right? We shall let our t to be tan half x. So this step is the same, so it means that our dt will be a half sec squared a half x dx, and here we can have the 2 dt is equals to 1 plus t squared. This one, of course, I've shown you in the previous example how it comes about. Then it means that your dx will be twice 1 plus t squared dt, which implies that our integral of sec, remember, to get a sec x, it is the same as 1 over cos. So we have 1 over cos x dx. Now, 1 over cos x. But remember, cos theta itself, or cos x itself, is 1 minus t squared out of 1 plus t squared. So implying that, it would imply that now when we have 1 over cos, you also take the reciprocal of this. So we shall have 1 plus t squared up, then 1 minus t squared down. So we shall have the integral of 1 plus t squared out of 1 minus t squared, then times dx, which dx is 2 over 1 plus t squared, then dt. So when these two cancel, we shall be left with the integral of 2 out of 1 minus t squared dt. Who can tell me what we are going to apply here? Class, who can tell me what we are going to apply here? Who can tell me what we are going to apply? We apply partial fractions because this is a difference of 2 squares. So just don't start letting, okay? So we shall say, still, this is the same as the integral of 2 out of 1 plus t times 1 minus t, then everything dt. This is the difference of 2 squares, making it a partial fraction. So we shall let our 2 out of 1 plus t in 1 minus t, we shall let it to be a over 1 plus t plus b over 1 minus t. And I will believe that some lessons helped us cover how to deal with the partial fraction. So it means that these two, okay, these two, when you take the LCM here, 2 will be the same as a into 1 minus t plus b into 1 plus t. So we can set, or we can put, putting t as 1, here it will go, so we shall get b. So it means that our b here, of course, if t is 1, a has gone, so we shall have 1 plus 1, that is 2b is equals to 2, implying that our b is 1. And if we put t as negative 1, if we put t as negative 1, it means that here b has gone, we shall have 1 minus negative 1, which is 2a is equals to 2, and you get your a also as 1. So if you get your a as 1, now you can easily integrate the function you're given. It would imply that, before you go to integrating, imply that 2 over 1 plus t into 1 minus t is the same as a, which a has been gotten as 1. So it is 1 over 1 plus t, then plus b, which is also 1 over 1 minus t, implying that the integral of 2 over 1 minus t squared dt is going to be equal to the integral of 1 over 1 plus t dt, all right, plus the integral of 1 over 1 minus t, then everything dt. Now, when you look at this, when you integrate this one down, of course, when you differentiate this, you get 1, so it is ln of 1 plus t. We have ln of 1 plus t. Then here we shall get minus ln. It will be minus ln because of the negative here. So it will be minus ln into 1 minus t. Because when you differentiate it, you get negative 1, and yet here you have 1. So it is negative ln of 1 minus t, then plus a constant of integration. But remember, you have what t is equal to. You have t, it was, question is in terms of x, so you have t as tan a half square x, okay? So we shall just substitute, and we shall have, our integral. After substituting, we shall say therefore our integral of sec x dx is equal to, now we substitute t as tan a half, so it will be ln 1 plus tan half x minus ln 1 minus tan half x, then of course plus a constant of integration. But remember, ln, we treat ln as logarithm, and the fact that you have ln then minus ln, so you put under one natural logarithm, and then you say 1 plus tan half x over 1 minus tan half x, then everything plus a constant of integration. So that is what we come up with after integrating a sec x. We use the T-substitution. Okay. That is what we are having. We are going to do another example, because in this lesson, I want to push in a way that I just be left with work of one lesson to complete this integration, and then we move to differential equations. Now, after having covered all this, After covering all this, we can go on to another example, maybe in case there is a question. If there isn't any, then allow me go to another example where I'm going to integrate sec 3 theta d theta. There is nothing that has been, there is nothing different here. There is nothing different here from what we've seen, only that now they have brought in a 3, but you can't fail to get means of treating a 3, okay? So in other words, now the fact that they have taken us to sec 3 theta, we shall let the value of t to be equal to tan half, now not theta, but tan half 3 theta. Tan half 3 theta is the same as tan 3 over 2 theta. 3 over 2 theta. Okay, you open 3 over 2 theta. So now, if we have t as tan 3 over 2 theta, it means current. Now we have gotten that our t is tan 3 2 theta. Now, if you differentiate both sides, you get the t as 3 over 2 sec squared 3 over 2 theta d theta. Okay, so we need to do all we can to get, of course, this 2 will multiply here, so it will be 2 dt is equals to 3 into sec. Sec is the same as sec is the same as 1 plus tan squared. So it will be 1 plus t squared theta. No, it will be 1 plus t squared, then d theta. Because why am I saying 3 into this? This 2 as cross multiply, this side is multiplied. So here we have 3 sec squared 3 over 2 theta d theta, but sec squared is the same as tan squared. And we have tan already, which is tan 3 over 2. So I've just done substitution. And from here, we can get what our d theta is equals to. Our d theta will be equal to twice the t over 3 times 1 plus t squared. So after getting this, we can now directly match to our sec of 3 theta d theta, and our sec 3 theta d theta is very easy in a way that you can easily express, or you can easily work on a sec, and you know that a sec is the 1 over cos. So it is 1 over cos 3 theta d theta. Okay, it is 1 over cos 3 theta d theta. Interesting. Now, having in mind that a cos theta is 1 minus t squared over 1 plus t squared, it means that 1 over cos, it will be the reciprocal. So this will be the integral of the reciprocal, which will be 1 plus t squared over 1 minus t squared times d theta, which is 2 dt out of 3 into 1 plus t squared. This one will go with this one, so that you remain with, you're going to remain with, if this one cancels with this, remain with the 2 over 3. I can move 2 over 3 outside, 2 over 3, then the integral of dt. Now here we'll be left with 1 over 1 minus t squared, then dt. Now, of course, here, like we did, also here you have to do what we call the partial fraction. I can move this to here for easy calculation. So I can, for me to calculate easily, I can bring back that 2, and I say it is a third, 1/3 of the integral. Then I say 2 over 1 minus t squared dt. Still, this is very okay because here you can easily integrate. We had already in the previous example seen how we work on this, so allow me just quote it, but as you're doing, for you, you have to do all, okay? Allow me quote it, allow me say that from partial fractions, the third integral of 2 over, of course, it will be 1 plus t squared and 1 minus t squared is going to be equal to, of course, dt is going to be equal to a third integral, since I've already expressed in the partial fractions in the previous example. So here, allow me just write 1 over 1 minus t, okay, dt, then plus a third also integral of 1 over 1 plus t, then dt. All right, so this is going to be, because this is negative ln, so it is negative a third ln 1 minus t, then it will be plus a third ln 1 plus t. Yes, Emily? Yes, Emily?
Excuse me, sir.
Yes.
Teacher, where are they getting this one from, these squares?
Oh, sorry. That's good. That is a good observation. It was just a difference of 2 squares, so it is just 1 plus t, right? And 1 minus t. I didn't do it from the first principles, the fact that we had just done the partial fraction of this, but that's a very good observation. Thank you. Okay, so here it's going to be negative a third ln 1 minus t plus a third ln 1 plus t, then plus a constant of integration. This one can lead us to concluding that the sec integral, rather the integral of sec 3 theta d theta, is the same as a third ln. Since I'm subtracting, then I will begin by writing this. Third ln 1 plus t, but I know t as tan half 3 theta, or tan 3 over 2 theta, so it will be 1 plus tan 3 over 2 theta out of 1 minus tan 3 over 2 theta, then of course plus a constant of integration. So that is what we can have. That is what we can have. That has been interesting. So let's do examples that involve some other logics or the application of what we have just looked at. Okay. All right. So what we are going to do, let's do some other example. So this example 3, or example 4. Let's integrate this. 1/3 minus 2 cos t dt. Now, if they give you exactly in terms of t, now don't say let t equals to tan½ t, because they have already given you that it is in terms of t. So if it is in terms of t, you use another variable, okay? We use another variable, and we are going to see that here, maybe one can say let p, I can let p to be tan½ of what I'm expressing, which is tan½ t, okay? So if my p is tan½ t, then I can differentiate both sides. It will be dp is equals to 1/2 sec² t, then the what? The t. All right, so in this particular case, my 2dp would be equaling to, my 2dp would be equaling to sec², which is already p, so it will be 1 plus p², because if p is tan½ and you know that sec² is 1 plus tan², so it means that it will be 1 plus p², then dt, and in this case I can get my dt as dt equaling to 2dp out of 1 plus p². Having all this, now I can come and substitute. You need to come when you know what a cos t is equal to. We need to know what a cos p is equal to. It would imply that the integral of 1/3 minus 2 cos t dt will be equaling to the integral of 1/3 minus 2. But we've seen that our cos t, in this case, we are going to express it in terms of p. We're going to express it in terms of p, and it's going to be 1 minus p² out of 1 plus p². This is what cos t is equal to. Then times dt. Our dt is twice dp out of 1 plus p². All right, now what you need to do here is to ensure that you simplify this. You need to ensure that you simplify this. Okay, you need to ensure that this work here is simplified, because if I'm to show you those, what I may call the baby steps of coming up with the final thing here, of course, I will continue with I'll continue from there, but simplifying this here will see you having 3 down, 3 minus 2 plus 2p² out of 1 plus p². This one here only. So the LCM is 1 plus p², so it is going to be 3 plus 3p². I've multiplied this one here, then minus 2 plus 2p² out of 1 plus p². I'm just simplifying this. So 3p² plus 2p², then it goes to 5p². So we shall have then 3 minus 2, that is 1. So we shall have 1 plus 5p² out of 1 plus p, squared. That is this one, only this one. So it means that our integral from this step is going to be equal to the integral of 1 over the whole of this as reduced to 1 plus 5p squared out of 1 plus p squared, then of course times 2 dp out of 1 plus p squared. So you have to be very technical in that this one here will need to move up, okay? Because you have 1 divided by 1 over this. So this one moves up and it cancels with this, okay? This one will move up. I want you to look at it as 1 divided by 1 plus 5p squared out of 1 plus p squared. So when you check the reciprocal, the 1 plus p squared will move up and will cancel with this. So this integral will end to the integral of 1 over, actually not 1 over, it will be 2 dp out of 1 plus p squared, 1 plus 5p squared, sorry. A 2 can be moved out and it is going to be 2 integral of dp out of 1 plus 5p squared, which takes us to tan substitution. This one will take us to tan substitution. And as we covered the tan substitution, since we already have a 1, we just need to work on this. So we shall say this is the same as 2 the integral of dp over 1 plus root 5p, then we square the whole thing, so that we can let our root 5p to be equal to maybe tan theta, okay? So I can say let our root 5p equaling to tan theta, so that our root 5 dp, because here you have to differentiate with respect to p, and this side you have to differentiate with respect to theta. So our root 5 dp, members, if you missed this, I guess you can go, good thing I recorded lessons over this, you can go and check on the areas where we differentiated, or rather where we integrated using tan substitution. So this is sec squared theta d theta, all right? So we can get our dp as equal to sec squared theta d theta out of root 5. So that when you substitute, your integral is going to become the integral of dp, which I'm going to substitute as this, then over 1 plus root 5p. So it is going to be, let me first say 1 over 1 plus root 5p. Remember, root 5p is tan, meaning if it is square, it will be 1 plus tan squared at theta. Then dp, we are multiplying dp, which dp is sec squared theta d theta, everything is out of root 5. 1 plus tan squared is the same as sec squared theta. So this one will go with this, and we shall be left with the integral of 1 over root 5 d theta. It's better you move the 1 over root 5 out, so we shall have 1 over root 5 integral d theta. When you integrate d theta, you get theta, so it will be 1 over root 5 theta plus a constant of integration. But from here, our theta will be equaling to tan inverse of root 5p. So it's going to be equal to tan inverse of root 5p, all right? Oh, I'm leaving out the other 2. I'm leaving out the 2. So it is going to be here, I'm supposed to come with a 2, with a 2, with a 2. So it is going to be 2 out of root 5, 2 out of root 5. Then instead of theta, here you can make theta the subject as tan inverse of root 5p. So it is going to be 2 over root 5, okay? Then tan inverse of root 5p, then of course plus a constant. But your answer was being given in terms of t. So you have to take it back to t, where we have our p as tan half t. So you will substitute, so it will be 2 out of root 5 tan inverse, okay, of root 5. Then instead of writing p, you write tan half t. Then everything plus a constant of integration. So that would be your final answer. In some cases, you may be calculating, and here it comes in as a completing square question. You have to reflect back and you see how we were dealing with the questions that have got the difference of 2 squares, okay? So that does not give you time. If there could be a question, I can listen to it. Yes, Emily.
Teacher, that part of letting the root of 5p equal to 10, I'm a bit confused.
Hey, now that one we covered it when we were looking at tan substitution. I will send you a video. You watch the details of this. But when the function is in this form, when the denominator is in this form, we use tan substitution. There are 2 substitutions we make use of, and that is the sign substitution and the tan substitution. So it is a very wider thing. It's a very wider thing that you need to get from first principles. I will send you the details, maybe you watch over it. But we use tan substitution because of the nature of the function that we have at this moment. So to stimulate your thinking, I'm going to give all of you this question. A moment. I'm going to give all of you this question, and for it, as you're working it out, it comes in with the sign substitution. So I want you to reflect back as you're doing this question. You first look at the fact that maybe you can do the calculations by sign substitution. So here, I want you to integrate 4 over 3 plus 5 sine theta d theta. I think I should do this because I have very many questions you can do. Let me do this because I wanted us to have also highlights on some other case. If I do that question, it means that for you, I'm going to do this. Then for you, we'll do this. It was very specific and clear in some UNEB question paper that using the substitution, t is equals to tan a half x, evaluate the integral from 0 to pi over 2 dx of 1 plus sine x plus cos x. So I would expect that question to be done by you people. Okay, you'll do that. Let me also do the first one. Let me do the first one. I'm going to do it very fast so that we can have a look at another case, but however much I'll be fast, I really want you to understand it. I really want you to understand it. Okay. Yes, Emily.
Teacher, that pi over 2, is it a limit or it's outside
a limit.
the integral?
It's a limit.
Okay.
0 to pi over 2. It's a limit. Okay, so members, let me do the first one. Now, for this case, we are having the integral of 4 out of 3 plus 5 sine theta. Now, the theta, of course, we shall let t to equal to tan half. Since I'm dealing with theta, it will be tan half theta. So my dt will be a half sec squared, a half theta d theta. All right. It would imply that my 2d theta, okay, from here, I guess we have learned how to express it. So 2d theta is going to be equaling to sec squared, a half theta, but sec squared is the same as tan squared, which tan squared would be t squared. So it will be 1 plus t squared, all right? Then d theta, implying that my d theta is going to be equaling to twice dt over 1 plus t squared. All right, implying that my integral of 4 out of 3 plus 5 sine theta, the theta is going to be equal to, I can move out of 4, then the integral of 1 over 3 plus 5 sine theta, we know is the same as 2t out of 1 plus t squared, then times d theta, which d theta is 2 dt over 1 plus t squared. You need to be very, very, very technical on evaluating that. So this is the same as 4 integral. Of course, here you have to take the LCM. So it is going to be, the LCM will be, this is of course 10t, then the LCM is 1 plus t squared, which will multiply in 3. So it's going to be 1 over 3 into 1 plus t squared, then plus 10t, then out of 1 plus t squared, then times the theta, which is 2 dt out of 1 plus t squared. You can really see that by taking the reciprocal, this 1 plus t squared will move up and it cancels with this. So I am going to be left with, 4, then integral of 1 over, this will be 3 plus 3t squared plus 10t, 3 plus 3t squared plus 10t times 2 dt. I can move this 2 so that it becomes 8. So I will have 8, the integral of 1 over 3t squared plus 10t plus 3, then dt. Now this one should take you back to what we saw when we are when you were looking at completing a square. Okay, you should be in position to complete a square in such a function. So if I say this is the same as 8 integral of 1 over, if I'm to complete a square, first factorize that 3, so it will be 3 into t squared plus 10 over 3t, then of course plus 1, right? Then dt. If you're not very sure, you can do it as side work and you bring, because for us we need the completed square of this function. Okay. All right. So now this is going to be 8. This 3 I can move it out so that I have 8 over 3. The integral of 1 over. Now, when you're completing a square, of course, we shall first write. Let me remind you. When you're completing a square, we're having t squared now plus 10 over 3t plus 1. So we write t squared plus 10 over 3t. Here we shall put something, then of course plus a 1. Okay, but what we put here is a half coefficient of x. A half times the coefficient of x. Coefficient of x is 10 over 3, but that coefficient of x we squared it. So actually it is a half coefficient of x, then everything is squared. So a half coefficient of x, this is 10 out of 6, 10 squared, which can be reduced to 5 over 3 squared, okay? So we shall put here 5 over 3, then squared. Then after, of course, we add half coefficient of x. So what we have put here, let me repeat this step for you guys. We say t squared plus 10 over 3t plus a half coefficient of t squared, which became 5 over 3, then squared. Then after doing that, we add the one we add. Then for equality, we shall subtract what we added, which is 5 squared over 3, which is 25 over 9. So that is what we are having, 25 over 9. So to complete a square here, we shall have t plus 5 over 3 squared, then 1 minus this, it will be minus 16 out of 9. So that is what we are going to bring and we put here. So if it confuses you really, let's go and practice how we can easily complete these squares, okay? So it's going to be t plus 5 over 3 squared minus 16 over 9. Yes, Emily?
Teacher, that part of 3t squared plus 10t plus 3, like what if I express them in terms of partial fractions?
It is impossible. Can you get factors?
No, like I get the value, like that thing of solving quadratics, and I get the values, and I'll be like maybe t minus 1.
If it can't be
bracket
factorizable, you may not use partial fractions here, but instead you complete a square and use the appropriate substitution.
Okay.
Okay, so now from here, what we do is going to be 8 over 3, the integral of 1 over 8 over 3 integral of 1 over, I can bring the negative 16 over 9 first. Negative 16 over 9. Then I say plus t plus 5 over 3 squared everything dt. Well, now here, as far as I'm aware, I'm going to transfer this step to another board. Okay, I'm transferring that step. I'm continuing with it to another space. So first capture this, and then I continue. This implies that from the step I've been having, I said we are at this step of 8 over 3, then the integral of 1 over negative 16 over 9, okay, plus t plus 5 3 squared then dt. Now looking at this, I can create a 1 so that I easily substitute the sign substitute. I can use the sign substitution. Okay. Okay. Now to do that, I will factorize. It will be 8 over 3. Okay. It will be 8 over 3. For it to create a 1, it means that you have to factorize 16 over 9, negative 16 over 9. So you'll be having 8 over 3 outside. If I'm to put it outside totally, I'll be having 8 over 3 divided by 16 over 9, but of course negative, which will be 8 over 3 times the reciprocal, negative 9 over 16. So outside, I'll have 8 over 3 times negative 9 over 16. Then the integral, okay, the integral of 1 over, here I've already factorized this out, so I will have 1, okay, I will have 1 minus, I have to divide this by what I factorized out. So it will be minus this, of course I'm dividing by negative, but because I'm dividing it, still it will be the reciprocal, which will be 9 over 16 of t plus 5 out of 3 squared. Give it time, give it time and see what I've done. Give it time and see. You may have questions, but first give it time. As pure mathematicians, give it time and see. If we factorize out 16 over 9 and you want to put it out, it means that you will be dividing it by this, which will turn out to be a reciprocal. Then still, when you, because you have moved it out, now here you have a 1, but because it's a negative, it means that you will have to divide it on this so that you equalize it. Meaning that by this one, mere entering inside, it is going to be the same as what we have. Okay, so that one, give it time and see it along. See it along. Now, when you look at this, this is 2. This is a half. This is a half, and this is negative 3. So it is going to be negative 3 over 2 outside. Then the integral of 1 over, this one will be 1, okay, minus, but because I want it to be a square, allow me say 3 out of 4 into, okay, I can say, let me use the curly bracket, 3 out of 4 into, you can say 3 over 4 into t plus 5 over 3, then everything squared, then the t. Now here, this can guarantee me to use sign substitution. Why? Because here I'll be having 3 over 4, this, I can let the whole of this to be sine theta or sine x. So from here, allow me say that let 3 over 4 into t plus 5 over 3, all right, be equal to sine x. So that when you differentiate either side, because this will be 3 over 40, then 15 over 12, but when you differentiate, it will be 3 out of 4 dt is equals to, when you differentiate sine, you get positive cos x dx, implying that my dt here is going to be equaling to 4/3 of cos x dx. I come with this one, I substitute it there. So I'm going to have my integral as -3 over 2, integral of 1 over 1 minus, the whole of this one I rate it to be sine x, meaning since the square, it's going to be sine squared x, times dt, which dt is 4/3 cos x dx. I'll move this one out. This will be -12, this will be 6. So it will be -12 over 6, which is -2 outside, integral of 1 minus sine squared x is the same as cos squared x. All right, so it is going to be 1 over 1 minus sine squared x. But from the identity sine squared x plus cos squared x is equals to 1, we can get sine squared x as 1 minus cos squared x. So it's going to be 1 minus cos squared x times cos x. Cos squared x. Oh, sorry. We have 1 minus sine squared x. It is the same as cos squared x without a 1. So this is cos squared x times cos x dx. This one will leave us with the -2 over 1 over cos x, 1 over cos x dx. But 1 over cos x is the same as sec x. So this is -2, the integral of sec x dx. We've already seen what a sec x is. This is the same as -2, all right? -2. Ln, because a sec x is ln 1 plus tan a half x out of 1 minus tan a half x. Then of course, plus a constant of integration. And put it under one bracket. Plus a constant of integration. So that is the answer. So such numbers, you have to be technically smart when you're doing them, and you have to flow very, very, very well and appropriately when you're dealing with them. Captured that, but I want to give you one can also integrate this, can evaluate from 0 to 2/3 pi of 3 over 5 plus 4 cos x and others. Okay, so allow me to take you to cases. Allow me take you to cases where we are integrating functions which contain a square. That is just a simple difference that we are going to look at. And then we see what the future is holding. They are very easy, only that some simple logic is carried out, okay? And that simple logic is what I'm going to show you. So the other one was the first case. Case 2. When you're integrating the trigonometric functions which contain a square of sine x or cos x, for squared functions of cos x and sine x, we use tan substitution still, but we let t to be equaling to tan x, not tan half. For squared functions, we substitute t as tan x. All right? We substitute tan x, meaning that for those functions like sine squared kx, where you're having some angle like 3, sine squared 3x, or cos squared kx, we shall entirely be using t equaling to tan kx. So we respect that very angle. So in other words, here we are not using tan half. When we have squared functions, we substitute t as tan x. We are going to do some examples like 2 because of the time I think we'll be getting done. We are going to do like 2 examples and then we see how we can move, okay? Let's do examples. Find 1, the integral of 1 over 4 sine squared x minus 9 cos squared x dx to integral of 1 over 3 plus 5 sine squared 5 theta d theta 3 integral of sine squared 3x over 1 plus cos squared 3x dx Okay, now for this one, for these ones, they have given you squares. So it is you to take them to the, because we are going to substitute tan, since we are in terms of tan, you have to ensure that you do the needful to convert these functions in either tans or sec. Okay, now, for example, for that Roman 1, you have 4 sine squared, 9 cos squared. For you to convert it to the case where you need it, we shall be dividing by cos squared. The numerator and the denominator. We shall divide it by cos squared. In that, if you divide here by cos squared, you have tan squared. And if you divide by cos squared, you will just have 9. Okay? And this one, when you divide 1 by cos squared, you will get sec. So you ensure that it keeps in that form. Here I will be dividing by cos squared 5 theta. Here you'll be dividing by cos still. So to take it back to take it in terms of sign where you need it. So here for Roman 1, I will say dividing the numerator and the denominator by cos squared x means that the integral of 1 over 4 sine squared x minus 9 cos squared x dx is going to be equal to the integral. When you divide the numerator, that is 1, by cos squared x, it is the same as 6 squared x, out of, when you divide this one by cos squared, you get 4 tan squared x, and when you divide this one by cos squared, you get 9, then dx. That is the first step we have to do. But a sec squared itself is the same as 1 plus tan squared x over 4 tan squared x, then minus 9. Of course, dx. Now, looking at this, now we can let very well. You can say let t equals to tan x. You let t to be equal to tan x, not any other thing, implying that your dt is going to be equal to sec squared x dx. All right, so our dt is, but a sec is 1 plus tan squared, meaning 1 plus t squared dx. This one can lead us to have our dx as dt out of 1 plus t squared. I'll come with that and say that my integral now, my integral of 1 plus tan squared x out of 4 tan squared x minus 9 dx is going to be equal to the integral of, remember you've let t to be tan x, so it will be 1 plus t squared, because if t is tan x, then tan squared, it will be t squared, out of 4 t squared minus 9 times the dt, rather dx. Dx is dt over 1 minus t squared. It sorts out itself. 1 plus, sorry. This one cancels with this, so that you remain with the integral of dt out of 4t squared minus 9. This is a difference of 2 squares if you are very keen, okay? If you are very keen, this is the difference of 2 squares, which is the same as the integral of 1 over, this is 2t minus 3. So it is going to be 2t plus 3 times 2t minus 3. How does it come about? 4t squared minus 9 is the same as 2t squared minus 3 squared, which makes it a difference of 2 squares coming up with this. Then the t. All right, now here, partial fractions at work. Partial fractions at work. So we shall let our 1 over 2t plus 3, 2t minus 3 to be equal to a over 2t plus 3 plus b over 2t minus 3. Solving this, it means that 1 is equals to a into 2t minus 3 plus b into 2t plus 3. LCM, then you cancel the denominator. So this one, you can either expand and then you equate, or you can use elimination. If we let, now the fact that we covered partial fractions, I really believe that someone can either first expand it and then equate the coefficients, or one can put, for example, if I want to eliminate A, I can put my T as 3/2. Putting T as 3/2 will give you the value of B as 1/6. And when you put T as -3/2, it will give you your A as -1/6. How do I come to this? Analyze the function very well. However, if by inspection one cannot get these values, expand it. 2AT minus 3A, 2BT plus 3B. Then you factorize those ones of T, you equate. What I mean, one can as well do 1 is equals to 2AT plus 3 plus 2BT. Of course, it is this is minus 3A, 2AT minus 3A plus 2BT, then plus 3B. So that here one can say 1 is equals to those of T, factorize them. It is 2A plus 2B into T. Then even the constants, minus 3A plus 3B. Then we equate. The coefficient of T, this side we have 2A plus 2B, but this side we don't have the coefficients of T, so it is equal to 0. For the case of constants, of course, here you can divide through and you see that your A plus B is 0. You call it your equation 1. Then you equate constants. Negative 3A plus 3B is equals to 1. You solve these two simultaneously, still you are going to get the same values. So now, after getting my value of A and B as this and this, I can switch them to the expression. I can switch them to the expression, and I see what I really come out with. The expression now is going to become, since I've gotten A and B, I'm going to substitute them and have it as I'll have it as my integral of 1 over, it was 2t plus 3, 2t minus 3 dt is going to be equal to a 1/6 integral of 1 over 2t minus 3, then minus a 1/6 integral of 1 over 2t plus 3 dt dt. For this case, of course, to integrate this, of course, when you differentiate this, you can't get this. So don't rush to put it in. You can first do it aside and you see, if I have the integral of 1 over 2t minus 3 dt, how do I reach the final answer? How do I reach the final answer? Let your denominator 2t minus 3 be equaling to u. It means that your 2 dt, if you differentiate, will be equaling to du, meaning that your dt is going to be equaling to du over 2. Meaning that your integral is going to become 1 over, this one you let it to be u times the dt, which dt is du over 2. Can you move out a 2? Yes, so it will be a half integral of 1 over u du, which will be a half ln u. So meaning that here we shall have 1 over 6 times a half ln, but u is 2t minus 3. 2t minus 3. This is what the whole of this comes to this. Okay. Then after this, of course, you'll say minus a 60th. The same applies to this, times a half ln 2t plus 3, then plus a constant of integration. To simplify this, this is going to be 1 over 12 ln 2t minus 3 minus 1 over 12 ln 2t plus 3, then plus a constant of integration. So what does it equal to? We can factorize out 1 over 12 ln. So 1 over 12 ln 2t minus 3 out of 2t plus 3, then plus a constant of integration. The reason as to why I'm dividing is because I'm subtracting the logarithms. So that would be the answer. That would be the answer. Yeah, if you are clear with me, or if you're trying to understand this, type yes. If you're trying to understand, type some yes. If you're trying to understand, type some yes, that is good. Okay, so these things, it's a matter of giving them time. You do not need to rush over anything. So I'm going to do maybe my final example for today, if time allows. Let me do my final example for today. And that example is the one which appears as our second example, which is the integral of 1 over 3 plus 4 sine squared 5 theta d theta. What do I do, members?
It was 5.
Hmm?
It was 3 plus 5 sine squared 5.
It was 3 plus what?
Plus 5 sine squared 5 theta.
Really, let's do this. Let's take it like that, because I've already written it. Still, the answer has been the same. Like, that's the procedure doesn't change. So let's take this. The first thing is to make sure that we bring in the aspect of tan. Okay, so we need to divide by cos squared 5 theta. So dividing the numerator and the denominator by cos squared 5 theta, we shall have our integral of 1 over 3 plus 4 sine squared 5 theta d theta as equal to, when you get 1 by cos squared 5 theta, you get sec squared 5 theta over 3 by cos squared 5 theta. It will give you 3 sec squared 5 theta. Then this one will give you 4 tan squared 5 theta. Integral, then the theta. So this is going to be equal to sec squared is the same as 1 plus tan squared 5 theta out of, even here, it will be 3. Okay. 3 sec squared. So it's going to be 3 into 1 plus tan squared 5 theta plus 4 tan squared 5 theta d theta, isn't it? So this is 3 plus 3 tan squared plus 4 tan squared. So down we shall have 7 tan squared. So it's going to be 1 over, 1 plus tan squared 5 theta. Then 3 plus 7 tan squared 5 theta d theta. Isn't it, members?
Yes, it is.
Then we shall say let t equals to tan 5 theta. What will the t be equal to? 5, you bring a 5, then sec squared 5 theta d theta. Meaning that our d theta is going to be equaling to dt out of 5 sec, which will be 5 into 1 plus t squared. So that is what we are having. So we simply substitute. And on substituting, we are going to have our integral as I'm substituting here. It's going to be 1 plus, remember you let tan squared, tan 5 theta to be t, meaning it will be t squared here, out of 3 plus 7t squared, all right, times d theta, which d theta is dt out of 5 into 1 plus t squared. This one will go with this. Outside we have 1/5. We shall have 1/5 integral of 1 over 3 plus 7t squared dt. Who can tell me the substitution that we shall use there? Which substitution are we going to apply? This one is going to give us a we shall use term substitution after factorizing out a 3. Members, at this time, you should be able to look at a function and then you see which case am I going to rest here. Which case, don't rest yours, but which case am I resting here? So one can say this is the same as 1/5 integral of 1 over, factorize out 3, it becomes 1 plus 7 over 3 t squared. Put this one out, it is going to be 1 over 15, isn't it? If you factorize out a 3, it's going, of course, the t, it's going to be 1 over 15, okay? Then the integral of 1 out of 1 plus 7 over 3t squared dt, of which you can still write that one further as 1 over 15 integral of 1 over 1 plus root 7 out of root 3, then t, then everything squared. Because there is no way how you can use t substitution when this one is not expressed as a square. So that's why I put them under the root, so that I put under the square altogether, and it goes back to this if you want to put a square inside. So here you let that root 7 over root 3 t to be equaling maybe to tan theta. Okay, meaning that root 7 over 3 over root 3 dt is going to be equaling to sec squared theta d theta. So that your dt is going to be equal to sec squared theta d theta, but we shall be dividing by root 7 over 3, which will be root 3 out of root 7 on coming this side. So we substitute, it is going to be equal to 1 over 15 integral of 1 over 1 plus, all of this one is tan, meaning this is going to be tan squared theta, times dt, which dt is root 3 over root 7 sec squared theta d theta. This one, the sec squared, will go with the 1 plus tan squared because they are the same. Move out root 3 and root 7. So it is going to be root 3 out of 15 root 7. Okay, root 3 out of 15 root 7 integral of d theta is going to be root 3 out of 15 root 7. All right, 15 root 7. When you integrate theta, the theta, you get theta, of course, plus a constant of integration. This is going to be equal to root 3 over 15 root 7 theta. If you have tan theta as this, then our theta will be tan inverse of this. Okay, so we shall, let me include it here. Theta is tan inverse of root 7 over root 3 t. Okay, so theta, which is tan inverse of root 7 over root 3, then t. Now allow me bring my answer and complete it from here. I'm completing it from here. So this t, I already have my t as tan 5 theta because I have to overall take it back to where it is. So this is going to be equal to root 3 over 15 root 7 tan inverse of root 7 over root 3, okay, root 7 over root 3 t, which t is tan 5 theta, of course, plus a constant of integration. That is what we are having. That is what we are having. One can move it at that. One can move it up to this extent. And that is what we are having. If you've understood all I've done here, members, type a yes and we call it a lesson. If you've understood this, type yes and we call it a lesson. That's good. So you can practice most of these questions, and we are left with the one section in integration, which is splitting a numerator. So one lesson is enough for us to get through with this topic of integration, and then we see what the future will hold, either complex numbers or differential equations. I wish you the best. See you.